do a couple of examples involving the electric field made by point charges. And we remember that when we have a point charge, the electric field magnitude is given by this formula, which is related to Coulomb's law. And it shows that there is an inverse square relationship between the distance that you are from a point charge and the magnitude of the electric field made by that point charge. So in the picture you can see that there are 2 point charges here and here, and what we're looking at is the net electric field created by both of those point charges. So we're going to figure out a couple of things about those charges just from looking at the net electric field. And before we do that, you have to remember that the definition of an electric field, the definition of what these lines and vectors here are showing, is what would happen to a third charge, to a test charge that I place at any of the locations in the picture. So the rule is that the electric field direction is the direction that a positive test charge would experience a net electric force at each of these places. And the other rule is that the magnitude of the net electric field can be seen by how closely spaced, how densely packed the electric field lines are. Where the lines are closer together, that indicates a stronger net electric field, and where they're farther apart, that indicates a weaker net electric field. So just from looking at this picture, a couple of things that you should try to figure out. One is, can you figure out what is the sign of the charge of each of these 2 point charges? Think about that for just a second, and think about the definition of the electric field that we just mentioned. So if you think about it, you have to imagine what would happen to a positive test charge that I place next to each of these 2 charges. And the arrows would show you that a positive charge placed anywhere close to this charge, we're going to call this guy QT, T for top. A positive charge placed anywhere near there would experience a force directly away from that Q top, which means it would be repelled by Q top. And that's only possible if Q top is a positive charge, because like charges repel. So we know that Q top must be positive by that rule. Similarly, if you put a positive test charge near Q bottom, these arrows would show that any positive charge placed near here would experience a force towards Q bottom, would be attracted towards Q bottom. And because opposite charges attract, we know that Q bottom must be negative. So that's how we can tell the signs of these 2 charges. Now you might believe from looking at this picture that because the lines of the electric field seem to be drawn in towards Q bottom, that might be showing that Q top and Q bottom are attracting each other, but you need to understand that's not at all what these lines are showing. These lines do not show what Q top and Q bottom do to each other. The lines show what the net effect of Q top and Q bottom would be on a third charge, on a positive test charge. Alright, so we figured out that this charge is positive, this charge is negative. Another question we might have is, do these charges Q top and Q bottom have equal magnitude, or does one of them have a greater magnitude? So think about that for a minute, and if they don't have equal magnitude, how could you figure out which one has a greater magnitude? So one way to figure this out, if you think about the relationship between a charge Q and its electric field E, this shows that a greater charge will make a greater electric field if we're at the same distance from that charge. Now what we're looking at here is actually the net electric field made by both charges combined. However, if we're close to Q top, then we can understand that the electric field when we're very close to Q top is mostly due to Q top. The net electric field at any of these places close to Q top is not very much affected by Q bottom because we're kind of far away from Q bottom. And when we get close to Q top, his electric field kind of dominates the net electric field. So if you look at a point close to Q top, the net field is mostly the field of Q top. And we can see that the electric field lines there are very densely packed together, much more densely packed than if we're at a place close to Q bottom. So that would be one way to understand that since the electric field of Q top seems to look greater in magnitude than the electric field of Q bottom when we're at a small distance away from each one, then that suggests that Q top must be greater magnitude than Q bottom, and that would be a correct conclusion. Now that's one way to tell who has a greater magnitude. Another way that you should know how to explain is, let's pick a point that's not very close to either Q top or Q bottom. And since we want to be able to compare their electric fields, the best way to do that is to pick a point that's equal distance from each charge. So we're going to make the R from each charge the same. And to do that, I'm going to draw a line that's a perpendicular bisector of the line connecting the charges. So pick a point somewhere along that line. I didn't quite get a perpendicular bisector, but it's close. So, and let's just pick a point right here. All right, and I'm going to call that point P. And so this distance from here to here would be the radius from the bottom charge to P. That's how far the point P is from B. This distance would be the radius from the top charge to P, and those distances are equal. So now, if what this electric field, the net electric field line shows at point P, is that the net field is in a direction tangent to the field line at that point, which you can tell is this way. All right. Now that net field is created by the electric field of the top charge at that point, plus the electric field of the bottom charge at that point. And I'm going to draw those on a separate diagram here. I'm going to move my paper up just a little bit. So at location P, if you imagine that point and imagine what would happen to a positive test charge placed at that point, we know that the top charge would be repelling a positive test charge. So the top charge, if we were to draw his electric field vector at point P, would make an electric field along the line directly away from that top charge. So I'm going to try to draw that in my little diagram here. This would be the direction of the electric field of the top charge, because that top charge would be repelling a positive test charge. The bottom charge at that same location would attract any positive test charge, and so would make an electric field along this line straight towards the bottom charge. So the bottom charge would make an electric field kind of like this, E of the bottom at that same point. Now, what you can kind of see is these are competing a little bit with each other. We have to add these two together to find the net electric field. Now, if these were equal in magnitude vectors, then the net of these two would be straight down, because their horizontal components would exactly balance out. Okay? But we can see from the net field that, in fact, the horizontal components don't balance out. There is a net horizontal component towards the right. All right? And so, to show that on my diagram here, I'm actually going to take a little bit off of my electric field of the bottom. I'm going to make his arrow a little bit shorter, and that way you can see that the combination of these two vectors, E of the bottom charge and E of the top charge, is going to point not straight down, but sort of down and to the right. And if you actually wanted to find the exact direction of that, you'd have to make a parallelogram here out of these guys and find the diagonal of that parallelogram, which would be kind of like that. That would be our E net. But the point, so we're not going to go through the parallelogram right now, but the point is that we've just proved that E of the top charge is greater than E of the bottom charge when the distance from the top charge equals the distance from the bottom charge. Therefore, Q of the top charge must be greater than Q of the bottom charge, which is the same conclusion we had from just looking at the density of the field lines. All right, so going back to the picture here, we have understood that we have 2 point charges, a positive one and a negative one, and the positive one has a greater magnitude charge. So the other question we could ask about this picture is there anywhere in this picture where the net electric field made by those two charges is actually 0? Is there anywhere that these two vectors made by the 2 point charges could completely cancel out to make 0 net field? And I'm going to let you think about that one. It's not obvious from looking at the picture here where that point would be, if there is one, but I will tell you that there is such a place in this picture. Maybe you can guess where it is, but I'm not going to work that one out. You can think about that one. We're going to work out a different example of how to find where the net electric field is 0. So that's pretty much everything we can do with this particular pattern. Now we're going to look at a different one. We're going to look at this pattern. And you can see for yourself and make a guess which of these two charges is greater. I will tell you that in the software program that printed these electric field lines, it wasn't the same program that printed the ones I just showed you. And this software does not use the rule that where the electric field lines are denser or closer together, that indicates a stronger electric field. So don't be fooled by that on this picture. We're going to show that in fact the charge on the bottom of this picture is the greater charge, even though you might think from the way they drew the field lines that the charge on the top is a greater charge. So how can we prove that? Also, before we prove that, this software did not put any arrows on the field lines, so we can't tell whether these charges are positive or negative, but you should be able to tell something about these two charges. If you look at this picture for a minute, can you decide anything about whether these two charges are the same sign or different signs? Again, I'm going to call this will be our Q of the top right there, and this guy will be Q on the bottom right there. Okay, so hopefully you recognize that both of these charges have the same sign. Okay, we don't know if they're both positive or both negative, but we know they have to have the same sign. And that's not because, even though some people might believe that these electric field lines are repelling each other, that's not the reason why. Electric field lines can't repel each other, by the way, because electric field lines don't have any charge. So even though it looks kind of like they're pushing each other away in this region, they're not. You have to remember, though, that the electric field that we're looking at is the net electric field created by both of these charges. And what this shows is that there are no electric field lines that go through this region right here. And what that means is if there's no electric field lines here, that a positive test charge, if we put it right around here, would not experience any net electric force. Okay? And we're going to use that fact to determine which of these two charges, Q top or Q bottom, has the greater magnitude. In fact, we're going to find how many times greater magnitude it is. Alright, so let's call this our point P. I'm going to estimate a point right here where if you were to draw all of the possible net electric field lines from these two charges, none of them would go through that point. Alright, so that's my point P. I'm going to measure with a ruler the distance from the top charge to point P, and that's our R of the top, and that's about 1.5 centimeters. And I'm going to measure the distance from the bottom charge to point P, and that's about 3.5 centimeters. R bottom. Okay? And then I'm going to make a vector diagram at that same point P and use that vector diagram to figure out some information about the magnitudes of these two charges. I'm going to do that on separate paper. So we don't know the signs of these two charges. However, we're going to assume that they're both positive. We know that they both have the same sign, so I'm just going to assume they're both positive. It wouldn't change the the rest of the argument if I assumed they were both negative. Okay, so at point P on that previous diagram, we want to look at what would happen to a positive test charge. Well, Q top would repel that positive test charge, and that means that at point P, the electric field of the top charge points straight down in the direction of the force on a positive test charge. Q bottom would also repel a positive test charge, so his electric field would be up, directly away from Q bottom. And I drew these two vectors the same length because we know that at point P, the net electric field is 0. That's what's shown by there not being any electric field lines there. So what we're going to do next is write a net field equation. We're going to use our formula for the electric field of a point charge and plug that into a net field equation, which is kind of like the net force equation that we would do if we wanted to actually find the force on an object at point P. So the net field is the total of the electric fields. I'm going to choose my positive direction to be up. So that would be the electric field of the bottom charge, magnitude, minus the electric field of the top charge, magnitude. And we know that that net field is 0. So that means that the magnitude of E bottom must equal to the magnitude of E top. And because these are point charges, bottom and top, we get to use the Coulomb's law electric field formula, K Q bottom magnitude over R from the bottom squared must equal to K Q of the top magnitude over R from the top squared. So from this net field equation, we actually know these distances because we measured it. We can cancel out the K because that's the same on both sides. So while we can't figure out exactly how much charge Q top and Q bottom are, we can definitely see that the ratio Q bottom over Q top, that ratio, if I divide both sides by Q top, must equal the ratio of R bottom over R top.
And we measured those distances. This one was 3.5 centimeters. This one was 1.5 centimeters. And if you plug that into your calculator, you'll find that it's 5.4, the ratio of those distances squared. So this demonstrates that the charge of the bottom must be 5.4 times more than the charge of the top in magnitude. So going back to our original picture here, that's why, so the reason that we can tell that Q bottom is greater magnitude than Q top is because the point where the net field is 0 is farther away from Q bottom and it's closer to Q top. So that's how these two vectors can end up being equal in magnitude, all right, even though the distance from Q bottom is greater than the distance from Q top, is that the magnitude of the charge of Q bottom must be greater than the magnitude of the charge of Q top. All right, so that's pretty much everything we can figure out about the two charges in this situation.